Okay, grade 10. So today is the day you get to transform all that knowledge you already know about trigonometry into those really cool waves that I'm sure you've seen on the posters of your teachers' classroom walls, or I'm sure you've heard people speak about trigonometric graphs before. So let's make it real for you today. Let's see how on earth do we go from right-angled triangles into those weird waves of graphs that you've seen before. Okay, let's just start at the basics. Let's start with what you know. I'm basically going to introduce this graph to you slowly but surely. We're going to take baby steps with the sine graph, and then because you'll have this foundation, we'll fly through the cosine and the tangent graphs. Right, anyway, do you remember that amazing destination we went to for a holiday? Yes, you do. It was Sokotoa. Sine theta is opposite over hypotenuse. Let's relate that to a triangle. Obviously, if theta is the acute angle, directly opposite theta is the vertical distance, and the hypotenuse is right there. Now, to get sine theta, we always put the opposite over the hypotenuse, and we simplify. We can even convert that number to a decimal. And then you'll see that if you keep theta the exact same size, but you increase the size of the triangle, in other words, we introduce a similar triangle, the ratio opposite over hypotenuse, sine is opposite over hypotenuse, will stay the same, regardless of how big the triangle you introduce may be. As long as you have the same angle in the corner of the triangle, the simplified version of O over H will give you the same value every single time. So for example, I'm just choosing random numbers here. Say you put sine 12 into your calculator. The answer you get when you press your equal button is the opposite divided by the hypotenuse simplified answer, no matter how big the triangle may be. Even if you have, say, sine 33, opposite over hypotenuse will be a specific value and it will never change. Sine 75, etc. So the ratio simplified will always be the exact same value for a specific angle that we're working with. So since we're developing a whole lot of constant values on the right-hand side of this equation, can't we link this theta to this ratio? Can't we perhaps make a graph? Because that's exactly what a graph does. It links the input values to an output value. In this case, our theta, then the degrees we choose to replace theta with, is our input value, while the simplified version of the ratio that our calculator just spits out at us is the output value. So if we have theta along an x-axis, we have the input x values, and then the corresponding y values actually represent the simplified version of. So let's give this a go. Do you remember the original technique we used to set up functions to sketch a graph when we're given the x and the y axis? We usually set up a table. So I'm starting from 0 and I'm going all the way to 360 degrees. Why am I not going beyond 360 degrees? Because this represents a full revolution. If you can remember from our cast diagram, once around the cast diagram represents 360 degrees. Now, in order to save some time and to not have to use my calculator 360 times in a row, I've just jumped between my x values by a step of 45 degrees. So I would like you now to take out your calculator and go to the sine function and pop in 0 degrees and close your bracket and see what the corresponding y value would be. Then do the same for 45, the same for 90, etc. Press pause and go find these corresponding y values. Actually make a table. If you have to set up your work so that you have a lovely clear heading called the sine graph, and then you set up this table yourself, go ahead and do it. I want you to generate these y values. I'm going to be silent for 3 seconds and then I'm going to carry on while you go and do that. Right, I hope you were diligent and followed my instructions and got these corresponding y values using your calculator. Another way we can do it is to use a table method on the calculator. We did discuss this during functions earlier this year. However, if you would like to be reminded of how to use your calculator to set up a table with x and y values, please let me know or let one of your teachers know, and we can definitely explain during our maths lesson over a live meeting. But for now, I'm just showing you this table right here. And of course, once you have a lovely full table of all these values, we can set up an x and y axis and plot the points. So if you have a look at the first column, when x is 0 degrees, our corresponding y value is 0. So that little bit of information can be plotted as this pink point over here. Then we're going to do the same for the next one. When x is 45 degrees, our corresponding y value is 0,707. Now that's a bit of a problem because I haven't yet made a scale on my y-axis. So let me go ahead and do that. Using a ruler, you can create a scale, and I'm making my scale just fluctuate up to number 1. So that notch over there represents a half, and then that notch over there represents 1. So 0,707 will fall somewhere between a half and 1, and so I plot it there as the yellow dot. Then a little bit of a hint, a little bit of a tip, maybe this is something you need to jot down because you're going to have to recall it later. When x is 90 degrees, the corresponding value is 1. That's a very significant point. Why? Because as we move along our table, when x is 135 degrees, the corresponding value is yet again 0,707. So as you can see, these points will form a curve, and here where x is 90, it seems like we've reached a maximum value. That is a very important fact that you need to remember for today. When x equals 90, sine equals 1, we've got a maximum value occurring over there. Anyway, let's carry on with our plotting. When x is 180 degrees, the corresponding y value is 0, so we plot it. When x is 225 degrees, the corresponding y value is negative 0,707. Now, do you see what's happening? When x is 270, our y is negative 1, another very significant minimum value. And then when x is 315 degrees, we back at negative 0,707. And once again, when x is 360 degrees, we back on the x-axis at 0. So have a look at this absolutely cool formation. If we go and connect the dots, do you see that you have voila, created a gorgeous sine curve? Now, I don't want you to be sketching this while I'm talking to you because I want us to now go over these significant values, the shape of the curve, the maximum, the minimum, the general features, and I want you to memorize these features so that you can sketch this curve from your head, so that you don't rely on your calculator, so that later on in your maths life you can have a stronger foundation of the knowledge of this graph, because it is going to be manipulated in many ways. So let's go over these very distinct characteristics of the sine graph. Firstly, what you see in front of you is called y equals sine theta. It's what I like to call the original sine graph. It is pure sine theta. We haven't manipulated the formula in any way. We have merely sketched it using our calculator. And now let's take note. If you have a look at this stretch of the x-axis from 0 to 180 degrees, we have what I like to call a mountain, because it goes up above the x-axis and down again. It looks like a mountain, right? So when I'm sketching the graph, I always go, let's first sketch a mountain, right? And the max value, the highest point on this mountain, is when y equals 1. Remember, a maximum value is always a y value. Then we continue our sketch, and do you see from 180 degrees all the way to 360 degrees, we have a valley. So it goes underneath the x-axis. So when you're sketching this, all you need to know is that you are going to make a beautiful mountain followed by a beautiful valley. Make sure they are the exact same size, not lopsided, and realize that that is what the sine curve is all about. It's a mountain followed by a valley, and the minimum value of this valley is y equals -1. It's as easy as that. Now what I'd like you to do is sketch this shape over and over again. Another thing I'd like you to notice, can you remember our quadrant 1 is from 0 to 90 degrees, and our quadrant 2 is from 90 to 180 degrees. Look at how sine, according to the cast diagram, is positive in quadrant 1 and quadrant 2. So the interval 0 degrees all the way to 180 degrees, sine is positive. What does that mean on a graph? Remember, positive, a function is positive when its y values are above the x-axis. And look at for which stretch of the x-axis the sine graph's y values are above, from 0 to 180 in quadrant 1 and quadrant 2. Isn't that so cool? Then in quadrant 3 and 4, from 180 degrees in a rotation all the way to 360 degrees in a rotation, do you see that sine is underneath the x-axis from 180 to 360? So in the negative quadrants, we have sine having negative y values. Right, I think that's all you need to know from this graph. I really cannot emphasize how important it is for you to be able to sketch this, and that's what we're going to do in the next slide. Here we go. If you are asked to sketch y equals sine theta, you can take the slow but accurate route. Okay, this is all depending on your personality. Do what works for you. The slow yet accurate route is to whip out your calculator, to press mode, and to put select number 7 for table. Then you enter the equation and you make your steps every 45 degrees, and the table will generate the sine graph for you. You make your start at 0 degrees and you make your end at 360 degrees. Okay, I've just given a quick summary of how to do the calculator, but I don't know why I get such a thrill from not being able to use the calculator, from knowing this graph really well and being able to sketch it from our head. So can you remember we started with a mountain? Another silly way for me to remember is I just say uppy, and then we follow then it's followed by a valley, a downy. So sketch an uppy, downy. Look at how I have absolutely no scale, no values on my y and x axes just yet. For now, it's just the shape that I am perfecting. Make a beautiful shape. You know how you had to practice forming the letter A in grade 1 over and over again until you could write letter A perfectly. That's what you need to do with the sine graph, because I know it looks easy, but try it yourself and you're going to see it is a skill to develop to make a beautiful mountain followed by a beautiful valley. They must be the same distance from that x-axis. It must look symmetrical. Okay. Anyway, once you get your mountain and follow it by your valley, now you can say, aha, I have drawn one full sine curve. So that at this point here, once you've reached this point on the x-axis, you can stop and you can label it 360. You have made one full revolution, so label it 360. Then use your logic. The end of the mountain and the beginning of the valley marks the halfway point. So what's halfway to 360? 180, of course. Now we've got two halves. We've got our mountain and we've got our valley. Let's think, what marks the middle of the mountain? Well, it would be smack bang down the middle right here, and it would be halfway to 180, which is, of course, 90 degrees. Let's go smack bang halfway between 180 and 360. That will give us the minimum lowest point of our valley, and that is what we call, oh, sorry, I'm jumping the gun here. The corresponding y value when x is 90 is the highest point, in which we saw on our previous slide that is the value 1. Then, if we go and see the middle of our valley, the lowest point over here is 270, because 270 is directly halfway between 180 and 360, and its corresponding y value will be a -1. So that is the process. Those exact steps is how you can perfect sketching the sine graph, by following the thought process, getting the mountain and the valley out first, marking the x-intercepts, marking the minimum and maximum values. You must remember that you can also, sometimes it's required of you to give the coordinates of the turning points. What do I mean by turning points? I mean this point where if you were walking uphill, the slope went from positive to negative, that would be the turning point when x is 90 and y is 1. Then you carry on walking along this hill. Now we're going downhill, downhill, downhill. Suddenly our gradient comes to a standstill, and it changes from a negative gradient to a positive one. That's the other turning point, and they represent the maximum and minimum y values respectively. Okay, I hope you are getting this. I hope you're enjoying it. I hope you're seeing how everything is intertwined and interlinking. It's quite fascinating. Remember that whenever you are required to sketch any graph, you always have to label the turning points and the x-intercepts. You will lose marks if you don't do it. Now, let's discuss a new word called the period. The period is the number of degrees through which the curve flows before it repeats itself. Say it to yourself 10 times over. The number of degrees through which the curve flows before it repeats itself. So basically what I'm trying to say here is that if this sine graph has a mountain and a valley by 360 degrees, if you were meant to continue, if you attempted to continue this pattern, do you agree that you would start drawing a mountain again? And so you would be repeating the sine curve. So the number of degrees through which this curve flows before it began to repeat itself was 360. So there's a fact for the day. The period of the sine graph is 360 degrees. Let's talk about the range of this graph. If we have to give, remember that a range is merely a set of y values where we state what the smallest y value that has a corresponding x value is, and then we state what the largest y value is. So it's minimum, semicolon, maximum. So for this one, our minimum value is -1, our maximum is +1. So another fact, it will never change unless we manipulate this formula. The range of sine theta is -1 to +1. Rightio. Another way of writing that is to say sine theta is sandwiched. It's always fluctuating between -1 and +1. Let's remember this is called set builder notation. Here you can say sine theta is greater than or equal to -1, but smaller than or equal to +1. I know you are just being overwhelmed with information today. So the next thing you need to realize is the next thing you need to know is something called an amplitude. Now, perhaps you've dealt with this in science, perhaps you've heard this word before. An amplitude always relates to waves, and I'm sure you'd agree that this sine graph looks like a beautiful wave. It is the distance from the center line to the maximum value. And also it's the same as the distance from the center line to the minimum value. Now, what is the center line? In this case, it is the horizontal line that cuts this graph in two perfect halves, that separates the mountain from the valley. So that x-axis is the center line. What is the distance from the x-axis to the maximum value on the y-axis? Well, it's 1. So the amplitude of this sine graph is 1. Okay, so let's see if you can remember how to sketch the sine graph. Let's run through it quickly. We have a mountain, we have a valley. We know that the significant x values are 90, 180, 270, and 360. Go and label the maximum value as 1. Go and label the minimum value as -1. As easy as that. That is y equals sine theta. Great stuff. Do it for yourself over and over again. Get used to this shape. Now, look at the heading of the slide. It says changing the amplitude of the sine graph. We just discussed what the amplitude was in the previous slide. It's the vertical distance between the center line of a wave and the crest being the top, or the vertical distance between the center line and the trough, or the minimum value. Now, let's pretend we were given a brand new formula. What if I asked you to sketch y equals 2 sine theta? What on earth do we do with that? Well, we can resort back to our table method. I'm going to do it just for the sake of this example, but then in the future I'm going to show you really don't need this table if you memorize this original sine graph really, really well. Okay, so if you want to, go put table format into your calculator, table mode, make your steps 45 degrees, start at 0, end at 360, and see what your calculator gives you if your formula is y equals 2 sine theta. Go double check that I'm doing this right. Basically, what I actually did is I looked back at the table in the first slide, or whenever we had that table, and I thought, well, if y equals sine theta has just been doubled, we've popped a 2 in the front here, then all those y values would just be doubled. So I went and I doubled all the y values. But then I placed spot the difference, and I noticed that there are some some points that didn't change at all. Those were my x-intercepts. So basically, these points over here, these x-intercepts are going to stay the same in my new graph. Then have a look at these purple arrows that point to something very similar to the original function. In the original graph, we know that sine of 90 should give us 1, and sine of 270 should give us -1. But here we're getting 2 and -2. So how on earth is that going to affect this sine curve here? Let's have a look. If you go and plot those points, you will see that the pink points stayed as they are. Look at how this x-intercept, this intercept, and this intercept is still there. However, the purple points caused this original black curve to be stretched up. And now, instead of fluctuating between +1 and -1, yes, you guessed it, the green sine graph fluctuates between +2 and -2. So what conclusion can we make about this value of 2 in front of the sine theta? It stretches this graph vertically. All it did was double every single y value, and so it doubled the what? The amplitude of the original sine graph. Now let's look at back to this black sine graph. If we were to now manipulate it and say, now I'm going to take my original sine theta and I'm going to pop a half in front of it. I'm sure you've picked up on the trend that now this graph is going to fluctuate not between 1 and -1, but rather between a half and -1/2. Let's look at what that graph looks like. Its maximum value is now a half, while its minimum value is now -1/2, because we changed the what? The amplitude of sine theta to now be a half. So basically, we can rework our formula. We can pop a little a in front of that formula, and that a stands for amplitude. A really useful formula that will help you find what a is. If I ever give you a curve and you need to find the a value, you can say that a will always be the difference between your maximum and minimum values divided by 2. Let's double check quickly. Let's check with the black curve. The maximum is 1. What is 1 minus the minimum? 1 minus -1 gives you 1 plus 1. Divide your answer by 2 and you get your amplitude to be 1, and that is the case for the original sine function. There's an invisible 1 in front of sine theta. Let's quickly try it for the big green graph. If we say the maximum value of 2 minus the minimum value of negative 2, 2 minus negative 2 gives you 2 plus 2, which is 4. Divide that answer by 2, and you end up with 2. And that is the A value, the amplitude value in front of the sine theta. Easy peasy. Okay, well done, grade 10s. You made it very far into this video. We're almost at the end. It's the last concept we need to just apply to the sine theta graph, and you'll be able to use this knowledge to complete today's homework. So let's have a look. Right here, as usual, I've got the original sine graph, and I want you to take notice of something. Have a look at the fact that the y-intercept of this graph over here is a 0. Look at that, the mountain, the foot of the mountain starts at 0. So this new function that I've introduced in purple on the right over here, if we were to have to sketch this, it is taking your original graph and it's just adding 1 to every single y value. So I've got and highlighted my significant points that form the shape of the sine curve, these pink dots, and I am going to take each of them and I'm going to shift them up by 1. So they will all move up by 1, and then if we connect those dots, you will form the purple curve. Do you see how sine theta plus 1 is the exact same shape as the original sine theta, but now the foot of the mountain is no longer at 0. The foot of the mountain is now at 1. So we still have an uppy, a mountain. And there at 180 degrees, where it would normally cut the x-axis, we have now met our center line of our wave, which is 1. So 1 represents the center line of the wave. It represents the vertical shift. Okay, so that 1 over there is very significant. It must always match up to what we know as the y-intercept, or the center line of the sine wave. What if we said y equals sine theta minus 1? Well, you guessed it. We know the original sine function, the mountain starts at 0. The foot of the mountain starts at 0. So for the blue sine theta minus 1, the foot of the mountain is now going to start at minus 1, because that negative 1 links up to that negative 1 in this new equation. We keep the curve exactly the same, but we bring all these significant points, those pink points, we bring them down by 1. And we end up with the blue curve just like that. So we can conclude that sine theta, not only can we manipulate, not only can it be vertically stretched or shrinked by applying an A value, the sine theta graph can also be vertically shifted or translated. Another word for shifting is translating. It can be shifted up or down depending on the value of Q. So Q represents a vertical shift. And a cool formula that's not the same as the formula in the previous slide, to get your Q value, or to double check what your Q value would be, you take your maximum and add your minimum and then divide by 2. Let's just quickly double check. Obviously our Q value for this one is positive 1. So let's take our maximum value. It would have been positive 2. I failed to label it here. Naughty, naughty. I would lose marks if this was a test. You have to label all your turning points and all your x-intercepts. So our maximum value would be 2, added to our minimum value 0. 2 plus 0 divided by 2 gives us 1. Hence our Q value was positive 1. What about the blue value? Blue graph, again, I'm going to lose marks. I didn't label my turning points. But you can see the top of the crest of the wave, the maximum value is 0. Added to the minimum value of negative 2. 0 plus negative 2 divided by 2 gives you negative 1, gives you the Q value. So there we have done vertical shifts. Are you ready to summarize this all and then jump into your homework? Okay, so if you have learned anything today, it is to please be able to sketch the basic sine theta. Know what it looks like. Do it 10 times over. I think that's actually going to be the first question of your homework activity. Sketch y equals sine theta 10 times over so that you know it very, very well. Then remember, you can apply transformations to this curve by multiplying it and by shifting it. You can combine the transformations. I did them on separate slides, but we can actually sketch graphs where there has been a vertical shift and a vertical stretch. Remember, A represents your amplitude, and your amplitude represents a vertical stretch or shrink, and that's the little formula for the amplitude. Another thing to note about the sign of A, if A is a negative number, then the curve has been reflected in the x-axis. Last but not least, we have Q, which represents a vertical shift. If Q is positive, we've shifted the graph up, and if Q is negative, we've shifted the graph down. Well done, you made it to the end of this video. Enjoy your homework.